As Sanaï said, my name is Mathieu Henri. I grew up in France, so you might notice some accent. Sorry about that. But actually, I come from Oslo, Norway, where I work as a JavaScript developer for Opera, the web browser company. They're pretty cool. I'm not a developer relations, yet they covered for me to come here. And during the day, I work as a JavaScript developer on Opera for computers. So everything we write there is all nice and clean. It's ES6, everything goes through code review, nothing goes to mainline without being checked by 1 or 2 developers and getting approval. And we ship code every week to about 60 million users monthly. So it's nice. And thanks to Opera and JSConf, I'm here today with my family. This is my daughter. She's crazy about animals. And we heard that the aquarium of Singapore is pretty awesome. So that's her plan for the day. And I hope one day she will come and speak to a conference like this to talk about her work and her passion. And that's what I'm here to talk about. I'm here to talk to you about tiny audiovisual demos and how to make them. So to go through the talk today, I will explain what I mean by tiny audiovisual demos and where I come from, then some general tips about how to make them, some wild tricks, and then it will be coding time. So, tiny audiovisual demos. What do I mean by that and where I come from? The JavaScript community knows me more as p01 for the small animations and creations that I make. I am into code golfing and creative coding. The things you see in the background, hope it's not too dark, are small productions that I made. They all range from 64 bytes, yes, bytes, to 1 kilobyte, and they all do some kind of animations or interactive things with sound or not. Code golfing is the art of reducing the code size to some ridiculous, like to the smallest possible. And creative coding is the art, or is the practice of using code to create art. I'm not the only one doing these kind of things. You probably remember Martin Klepper, who was here last year to talk about these kind of things. He's also into obtrusive code and artistic code. So he likes to make code that looks pretty on the outside and makes nice things. But this is not where I come from. I come from the demo scene. Maybe you heard about this. This is a subculture that was born about 31 years ago in Berlin. And basically, the essence of a demo scene is it's about packing the most bang for your buck with style. It's about making really cool animations and really push the envelope of the platform, no matter the platform. So this is where I come from. I'm into making cool things as small as possible and trying to push things in corners that you did not expect. This is what I mean and where I come from about tiny audiovisual demos. Now for some general tips. You have to focus. When you want to make a small demo, you have to focus. Really focus on the core of what it is you're trying to achieve. Don't try to diverge. Just do what you want to do, what you need to do, nothing more. So when you work around 1 kilobyte and even up to 4 kilobytes, the size itself does not matter. But the JavaScript community is crazy about frameworks. We heard the number of 150, 180,000 modules on NPM. This is not the place for that. Here you just go and create, and there's no need for libraries or frameworks. Just roll your own things. It's OK. As much as possible, you should try to use one primitive. It can be particles, can be lines, can be triangles, polygons, anything, squares, you name it. But using a single primitive will basically put one more constraint on you, and it will just drive your creativity. It will push you into corners you did not expect. And in the same idea, you should try to use a single formula, one single formula to drive the whole animation, to drive the sound, and to drive the visuals. That way, it makes things more coupled together and more in sync. So really, it is about focus. You need to focus and plan what you're doing. This is how you make tiny audiovisual demos. Now for some wild tricks. When you make animations, you often need to play with a bit of trigonometry just to make things move around, up and down, or in circles. So you will need to use sinus, cosinus, pi, and fractions of pi. And things don't need to be 100% accurate. It's OK to use approximations. The numbers you see above are just approximations of fractions of pi. And it's OK to use them. Things don't need to be 100% perfect. You're not shipping to customers. No one is going to die if things are slightly off by 2 pixels or 3 pixels. No problem. As you probably know, numbers in JavaScript and in many other programming languages are using the IEEE 754 standard. It basically defines how numbers are represented. They are represented in binary as a composition of powers of 2s and fractions of powers of 2s. And this leads to so-called floating point errors. In JavaScript and many other languages, if you do 0.2 plus 0.1, you don't get 0.3 as you would expect. You get 0.30004, which is right and wrong at the same time. This is right according to the standard. This is wrong from what you would expect. And this leads to things like this. You see this loop that goes from 0 to 10 with an increment of 0.1. It exits fine, and it's no problem. But at the end of the loop, I is not equal to 10. I is equal to 10.099999, which is correct according to the standard, but not what you would expect. But if you use the standard to your advantage and use an increment that is a fraction of power of 2, then all the numbers that are expressed during this loop are exact. They are exactly what you expect, and they are correct according to the standard. And that gives you some nice properties, like you can use modulos on that, and you can also do strict equality on values. Yeah. In this loop, you could do strict equality to 1 or 5 or 10 or 5.5, and it works. It works nicely. So use the standard, or know the standard, and try to use them to your advantage. It gives some really nice properties. There would be no audiovisual demos without music. And to do sound on the web, there's two ways. There's the Web Audio API, which we saw yesterday with Paul. It's extremely powerful. You can generate sounds, oscillators, load sounds, decode, apply filters, and these kind of things. And there's the audio element, which is much more limited. You can just load the sound and play it. But as I said, I come from the demo scene. And in the regular 1 kilobyte and 4 kilobyte demos, people pre-generate a big sound buffer at the beginning of the demo, and then they just replay it and run the visuals in real time on top of that. And that fits perfectly with the audio element. The code you see here is it's about 200 bytes of code. In itself, it's not important. The first 2 lines just set the header of a WAV file. The second 2 middle lines add to the sound buffer, and the last 2 lines play the sound buffer. That's all you need to get sound. And to create music, it's a bit like what we saw yesterday with Paul. The first line here just creates noise. Second line adds an exponential decay. And the last line adds that to the sound buffer. So what we get is like a white noise with an exponential decay. And that's basically a hi-hat. It just goes like this. So using small bits of code like this, you can build music. You will need colors, of course. And you will be tempted to use HSL to make colors shift to you across time. It's really nice, but HSL parsing is incredibly slow. Do 1,000 of these into your frame, and it will take just 10 milliseconds just to parse the HSL colors. This is unbelievably slow. You have 16 milliseconds to render 1 frame to get 60 frames per second animation, and you get just 10 milliseconds on that. So try to avoid HSL, and instead use something like this. Okay, it looks a bit crazy, but basically what it does, it just varies the R, G, and B component along the sinus, and it just detunes them by a third of a circle. So it does this U shift. Exactly the same, and it's an order of magnitude faster. Shadow blur. I've been using 2D Canvas for about 10 years, and for all this time I've been wondering, why would I use shadow blur for? Why would I use shadows of just simple shapes and paths? Until I realized recently that it's not just about shadows. You see this image? It's just triangles and shadow blur. You can make things glow and cast shadows, and it looks beautiful. And it's pretty cheap. So you can use very, very small things to add a lot to the visuals. When it comes time to compress your animation, the best technique so far is PNG bootstrapping. The idea is pretty simple. You take your code, you load that as a grayscale into a grayscale image, and at the end of this image, you add a bit of HTML and JavaScript. I would load the image, draw it onto a canvas, read the pixels, and then execute the code back. It compresses really good. And on top of that, because this is gzip in the end, or deflate, you can use additional tools like gzthermal to inspect the deflate stream and optimize your code to compress even better. So it's really, really good. The basic setup for that is, so at first line, you have your PNG image, so all the binary stuff. Then a canvas element, an image that loads hash, which is the image. And on load, you draw the pixels, read them back, add them to a string, and evaluate on the last line. So this is how you make tiny audio-visual demos. And I think it's about coding time. Yeah? Shall we do this? OK. So for today, I was thinking of revisiting an effect or something that I've not done in a while. I was thinking of doing some kind of plants growing or something that forks into like small threads and swirls around with colors and maybe looking a bit like fireworks or something like this and with sound. So if you try to think a bit about it, and now we should try to make something like this, shall we? Yeah? Sounds good? OK. Oh, that's my slide. And yep, this is the file. Let's say hello. OK, we've got hello. Everything works. So we need a bit of style. We need a canvas. An audio element, obviously. If we want to get sound, this is going to be useful. And some script. So let's style a bit our canvas. So first we need to make it full size, where it will be really nice. So top 0, left 0, full width, full height, and oops, just a background. It would be nice to get some kind of vignetting effect. It always looks nice, especially on a big screen. So we just use circles so that it fits the gradient into the whole viewport. Let's start from some kind of bluish gray in the center and shade of red on the outside. OK, so we got this gradient. OK, just bump it up a little. OK, so in order to draw onto our canvas, we will need a 2D context. Sorry, is the text big enough? Yeah? OK. Yeah? Sorry?
Turn off the flux.
The flash?
Flux. Do you have flux?
Oh, yes, I do.
Yes.
Sorry. Yeah, clever.
Yeah. Yeah.
Better?
Yeah.
Nice catch. OK. So, yeah, back to the 2D context. OK, so, and on load, we will have an update function. And we will render our visuals. So I would like a canvas. When I do animations, I really want to control the size of the viewport in which I'm drawing. That's why I know exactly that if I draw a line or a triangle that is 10 pixels, I know it will take exactly this percentage of the viewport Because if I use the current viewport size, then I have no idea how it's going to be rendered. I don't know if it's going to be rendered on a tiny phone or a giant screen on a 4K. So I always want to define the size of my viewport. So just a height of 512. Yeah, so this zero pipe basically casts the next things to, or the next expression to an integer. And I want basically to get the width to respect the aspect ratio, so that would be, yeah. And now we can do, we just go to the middle, set a nice color, very nice white color for just to display some debug output. In 0, 0 from the center. Okay, that's good. Everything works. So now it would be nice to initialize our things. So we can do if, yeah, as you can see, this is not your typical production project. We don't really care about globals and leaking and everything. It's fine. This thing is just gonna live for 1 minute, 2 minutes max. So if time was not defined, we just make sure the time is set to 0, our frame is to 0, and we can do time of the next frame to 0, and we can do plus and time plus equal 1/60, which is like 60 frames per second as our target frame rate. Let's see if that works. If we get, so that works. Except it would work even better if we request animation frames, so that our update function is called for every frame that is rendered on screen. So we get this small counter that is updated, the frame count. Everything good so far. So this is OK, but what we should do, actually, this is not correct. What we should do is use the current time. So we can use performance.now, which gives a time from when the application was started in milliseconds. So we divide by 1,000 to get this time in seconds. And we can do while the time is lower than the current time. And also, while our time is lower than the time of the next frame, then we'll just time plus equal 1 divided by, let's do something like this, like just increment in small values to just make sure that we reach the value we want. So when our time reaches the time of the next frame, then we increase the frame count and increase the time of the next frame to in 1/60th of a second. So things should really match the refresh rate of the application. Okay, everything's still fine. So I said that I wanted to display some kind of things that look like plants or branches that are twisting around and a little bit maybe like fireworks, like spiraling. So we need to do that. So we need an array of these little branches that have an X and Y coordinate, of course, an angle that will say where it's heading, an angle increment that will say in which direction it will twist, some kind of width that will say how thick is the branch, so that then we can know if it's a thick branch, it will not twist much, and it will grow a bit faster than smaller branches. So let's start with 8. We need an array of points or positions, and some kind of lifetime I will use. So here, let's say max 96. Okay, so, which line? Oh, yes, thank you very much. Thank you. So now we are in the time update, and we can also now update our visuals. So to do that, we will do for each vine, we will run a small update function that we will get the delta x. The delta x is how much we are moving forward in x, or how much we are moving in x coordinate. So since we are dealing with angles, this is for the x coordinate, this is the cosinus of the angle. We want it to move at some speed that is relative to the thickness of a branch, but not too much. And now we do the same for the y coordinate, so this is with the sinus. So dx and dy gives us how far we are moving for the next frame, for the current branch. So we add this to the x coordinate, similarly to the y coordinate, and we also need to increment the angle, so we do that. And we need to push the current point. So we push the x, which is the x value of the vine, the y, and it's really nice to have also the delta x and delta y that can be useful and allow us to do nice things. So we have the update of the visuals. Now we need to render them. So same thing. We look through the we look through the vines, do a small thing. So if we're on the first one, which has a width of 8, we will offset the current position to the current position, or the most recent position of the branch, so that things are always centered on the tip of the main branch. So that we'll be doing this. And now we can, we don't need this anymore. So we can begin, create a path. It's nice to know the number of points we are drawing. So we'll look through the points. Again, you see global variables everywhere, but it's fine. And we decrement. So we will look through the points from the most recent to the oldest. And we move the line cursor of the canvas to the position of the point we are looking at right now. And at the end, we stroke. So we get a nice line. Woohoo! Amazing. Yeah, but we are adding points all the time, so we need to limit a bit the number of points. To do that, we can splice the array and basically remove, say, 60 frames worth of points to have 1 second worth of points on screen. So let's see. Yes, so it shows the most recent 1 second worth of the branch. Yes, this is very nice. So now it would be, if we want the things to move around and to grow, we have to do that. So if we want to make them twist around, we can do that every 30 frames, for instance. So every 30 frames, we can basically set a random angle increments between 0.5 and 0.5. So every 30 frames, it should just twist around. Yeah. You saw that it goes a bit crazy. It really twists too fast. So it's because I forgot to factor the angle increment by the size of or by the thickness of the branch. So now this branch, which is supposedly very thick, should twist very little. Yeah. Let's try to do this. Yeah, that would be a bit nicer. So we also need to branch off, to fork this branch. So we need to do that as long as the thickness is greater than 1. We don't want like infinitely small branches. And we just branch randomly. So if a random number is greater than, say, the lifetime of a branch divided by some big number. Yeah. Let's see. Let's see if that works. We will need to push a new vine. And let's see how we define the first one. So the position of a branch, of a new branch, will be the position of a current branch. So same x, y, same angle, same angular speed. The thickness will be half the thickness, let's say. An empty list of points, because we're starting fresh. We don't want the current branch, or the new branch, to live longer than its parent. So we will use the minimum of the current lifetime of the branch, and some random value that is based on the thickness of the current branch too. So that would be v.l, which is the current lifetime, of the branch, and an integer value that is related to the width of the current branch times some factor. It's not really important, and some random value to make it vary a bit, so that the lifetime of this new branch will depend on the thickness of the current branch, and just wiggle a little bit, but it will not outlive the current branch. So let's see if that works. Yeah. Okay. So we've got this thing. Yeah. Yeah. We want things to live a little bit, or live a bit longer than 1 second. So let's put it to 5, and we see all these things. These things that we just saw spinning around, it's because we forgot to basically decrease the lifetime of the branches. So we'll do that. So to do the decrease of the lifetime of the branches, we just do a filter. And we just do. So this will basically decrease the lifetime and filter it. If the lifetime becomes falsy, becomes 0, it just pops out from the list. So that should be a bit nicer. Yes. This is. Yeah. Okay. Looks a bit nicer. Yeah. Also, okay, something that might be difficult to see now, unless we are lucky, is that the branches will basically die off completely when the lifetime is over. So then you will see this nice thread and just pops out, just disappears. So we should basically splice the list of points based on how long the current branch has to live. We can do that like this. And it should look a bit nicer already. Okay, we don't see it so much. Let's do this a bit. Yeah, divided once more by 2. The probability of branching off should make it a bit less crowded. Yeah, it looks a bit nicer. Okay, so it would be nice to add some color. So where we draw, we can do it up there. Yeah, we don't have so many branches on screen, so it's okay to use HSL in that case. It would be nice to have the hue of the branch depend on where it's heading. Since the hue in HSL is in degree and we deal with radians are basically from 0 to 6-ish. Multiplying by 60, it just maps to 360 degrees. Something hyper-saturated. And it would be nice also to make the thickness depend, the luminosity depend on the thickness, so that the thicker a branch or the older branch is, the brighter it is. So, and that is in percentages, luminosity. Yep. So you see some nice colors already. Yeah. Yeah. I mentioned shadow blur that makes things look really nice but really cheap. So let's do a bit of that. So we can set the shadow blur 0, and we need to set the shadow color. Shadow color. So now things should glow a bit, yeah. Yeah, that looks already a bit nicer. Yep, okay. So, yeah. Now, maybe we should try to add some sound. That would be nice. So, okay, water. Thank you. Yeah. When I was talking earlier, you saw these barbaric pieces of code, so I will not type that live, at least not the header of a WAV file, so I have a backup plan. So, this looks like a lot of cheating, but this array of note frequencies is basically so that you don't suffer through me trying to compose something that sounds melodic. It's, yeah, just to spare your ears, basically. And also, at the end, and you see this this line here that basically checks if the source of the sound of the audio element is set. It basically tells us, do I need to generate the sound or is it generated already? So at the end, in our where we are about to render the visuals, we can basically check this Boolean. And if we need to render the sound, we render the sound. Otherwise, we just render the visuals as we did before. Okay. Yes. Okay. So we will need to render the sound. So I just. Yeah. Yeah, that's okay. Don't even need that. So when we are in the time update, then when we are looping through our time, we need to check, okay, are we about to, do we need to create the sound buffer, or are we done with the sound buffer? So in this case, if we need to create the sound buffer, we do just that. Otherwise, yeah, it's okay. So we need a value that tells us how far we are in the current note that we are going to play. So we can do just time modulo 1, so it would be like one note will last 1 second. Let's do something like this. We take our, it was not indexed, and we can increment it when frac is 0. Because the value here, the increment here, is a fraction of power 2. It will align nicely on powers of 2 and everything. And so when I do modulo 1 and it's exactly an integer value, it will be 0. So I can do, if the fractional value of the time is 0, then it will increment our note index. We can do also code b plus 127. This will add the current value to our sound buffer, which is a string for now. And when we render the sound, here we create the header of a 16 kilohertz WAV file. We get the base 64 version of the sound buffer, append it to it, and play the sound. So str is the sound buffer, more or less. It's a string version of the sound buffer. So here we append new values to the sound buffer. And the value will be, let's say, time times frequency of a current note. The array of notes was 128 values, so doing the AND will basically look through in case we get or we request too many nodes. So doing this will give us a variable that will increment and follow the frequency of the node we desire. We can do modulo 1, which will give us a sawtooth. It will just get a value that will increment from 0 to 1 and then back to 0 and 1, like the sawtooth oscillator that we saw yesterday in Paul's talk. So we do that. And we need to add some kind of envelope to it so that we can shape the sound through time or through the duration of the note. And we will start at full intensity and just make the intensity of the note decrease linearly with the duration of the note. So our sawtooth will just decay linearly, no problem. And we need to apply a bit of volume, so let's say 16 for now. Hopefully everything works. Nothing works. This is... okay. Okay, let's see.
Check, there's supposed to be audio.
Sorry?
There's supposed to be audio.
Yes, we're supposed to be. We should be audio.
Should just bring up the volume for me.
Yeah. Is it the correct one?
Yeah, it's back in.
Yes, we did not do that.
Any software you can train.
This is the backup plan in case something like this happens. Let's keep a backup plan for now. We're not there yet. We still have 7 minutes. Okay. What am I doing wrong here? Okay, let's. Okay. Okay, I think the sound. Yes, of course. Sorry. What happens here is that I did not update the way that I check what is the current time. By current time, I mean how far do I need to render things. So now that I want to generate the sound, when I want to generate the sound, I want to generate frames for the max value. And otherwise, I want to generate until the current time of the sound. The current position of the sound. Did I set? Yeah, okay, let's say 48. Yeah, 24. Okay. Something I forgot to do here in the declaration of the branches is that I have this max that represents the duration of the animation in seconds. 1 second is 60 frames, and I forgot to multiply the lifetime of a branch by 60. So, yeah, it's a bit nicer. Okay, we're good. Okay. The notes are a bit slow, so maybe we can tempo that up. Beginning, you saw it sounded like low or like a low pace thing, and I kind of like it. So maybe we can do something like if the time, for every second that has 8 in the binary representation set, we can go fast, and otherwise we just go slow. Let's say even very slow. So at the beginning we should have it goes very slow, and then it should just go like. So we have one instrument which is like a sawtooth. We can probably make things a little bit nicer by adding another instrument. Some kind of a chord or some would be nice, and a slow-moving chord in the background would add a bit of depth to a sound. We can do that by using a sinusoidal oscillator. So we can do, again, we need to factor by time, and we can do note frequency. And if we want this thing to just go very slowly, we can use the time value and just shift it by 2 so that we get like every 4 seconds. When you do binary shift by 2 to the right, it just divides by 4 and gets the integer value. So we just change or move to the next note every 4 seconds. And we are inside the math.scene, so we need to go from 0 to pi over 2 to go full circle. So we do that. For this code, I don't really need an envelope. I just want this code to be always there. So no envelope, but it still needs a volume. Or we can do that. Yes. A small difference. Maybe I can. Yeah. And it would be nice also that this melody thing is not always at the same volume. It would be nicer to have a little bit of variation, so we can do that. Yeah, I'm just increasing the volume. It sounds a bit low for me. I don't know about you guys. So we just start from a base volume of 24 for the melody, and we will just wiggle around using a sinus based on the time. Let's say times, just the time, maybe. Yeah, that goes too fast. Or maybe not. Let's wait for the melody. Here, you see also that we are rendering all the points of our branches. It looks nice, but we can probably do something a little bit nicer. So here in the rendering loop, let's say that we pick 1 point or every 8th point. We want something that tells us, basically, here we normalize our position inside the list of points so that we know if we are at the very beginning, 0, or at the very end, 1, and multiply by 8, so that we just extend this small bit of line. And we can then start from the position of a point and use this E value that gives us how far we are inside the line to basically draw a tiny line that goes in the direction of the branch at this point in time. Let's see how that looks. So you see this bit of line that grows as a trail. And also it should look very nice when the branches die off, because then it should just go back. You saw this, you saw this onload handler. What about we add an image here? And then we just do this. Okay. Okay, everything's still fine. So on the first branch, it would be nice to have a little sprite, like some little guy walking along the branch. So let's do that. We need to rotate to adjust to the direction of the tip of the branch. So we rotate using the angle of the branch. Then we will need to restore that. And we will draw image, the current image. We can use the current frame index multiplied by 4 so that it goes a little bit faster. And yeah, my sprite sheet here is 128. The sprites are 16 pixels wide, so using and 112 basically gives me the X position of the current frame that I want to display. And the sprite is so 16 by 24. Let's render it at 0, 0, and like this. So we got this little person walking along the line, except it's not placed correctly. So now we can move it back on the line and offset it a little bit by a few pixels. Yeah, and now it's walking on top of the branch. Yeah. And yeah, it's just a little thing that adds some visuals. Yeah. Okay. And yeah, I think this is not too bad for about 30 minutes of code. Yeah, okay. Maybe it looks a little bit complex, but you saw that it's very small building blocks. It doesn't take too much to create things, and I'm sure you all have crazy ideas floating in your head. So don't be shy and just go ahead, and you can make these things. It's just use small things and add a bit. So in the end, I would just like to say thank you very much to JSConf for having me, and you can find me on Twitter, p01. I would like to say a big thank you also to Ferris from Outtracks, Ferris tweets now, who helped me with the musical direction for today so that I don't destroy your ears this morning. Thank you.
Thank you, Matthew. Thank you.